To interpret a quantum mechanical calculation so that we can predict the result of a measurement, we say that if the quantum mechanical calculation says the state of the system is psi, then the average value we will measure for some quantity A is given by the expectation value of A, which we write using this form so we can calculate it. And here, A, with the hat over it, is the operator associated with the quantity A. The measurement is a statistical process. We must repeat the experiment many times from the start, including the process that puts the system into the state, and take the average answer. We also find that every measurement we make returns a value corresponding to one of the eigenvalues, an, of the operator A. Not every measurement returns the same value. If we decompose a state into a linear combination of the normalized eigenstates psi n of the operator A, that is, a decomposition like this, a superposition of coefficients an times psi n added up over all of the possible eigenstates, then we find that the probability of measuring a particular eigenvalue is given by the modulus squared of an. This probabilistic result is known as the Born rule. If no external influence is applied in the meantime, any subsequent measurements on this system will always give the same answer, an, on measuring the quantity A. This behavior is called the collapse of the wave function. Measuring a quantity A appears to force it into one of its eigenstates, and as far as we know, this collapse is totally random, with those probabilities given by the Born rule. We can use this randomness for a specific practical application, which is the secure distribution of information. Conventional cryptography generally relies on it being very difficult mathematically to decode some information if one does not have the key. But quantum cryptography relies on fundamental properties of quantum mechanics, allowing the exchange of information with apparently absolute security. To see how this works, we first show that it's impossible to clone a quantum mechanical state reliably. The security of quantum cryptography relies on it being impossible to make an exact replica of an arbitrary quantum mechanical state of a system. For example, we might want to take an electron that's in a particular spin state and make another electron have exactly the same spin state, leaving the first electron in its original state. Equivalently, we might want to take a photon in a particular polarization state and make another photon with exactly the same polarization state, leaving the first photon in its original polarization state. In the case of photons, the two polarization basis states can be respectively horizontally and vertically polarized. A general linear combination of those two states is an elliptically polarized photon. Remember that an elliptically polarized light beam has some specific ratio of amplitudes of horizontal and vertical polarization and some phase difference between the amplitudes. In both these cases of electron spins and photon polarizations, we can, if we wish, write the state as a simple two-element vector with complex elements. So let's look at the proof of the no-cloning theorem then. We can show that starting from the first system being in an arbitrary state, so here's the first system, that's the 1, and the arbitrary state we'll think of first would be A, we'll call it here, and the second system in some prescribed starting state. So the second system is the 2, and the S means this very specific starting state. It always starts out in the same state here. Then we cannot, in general, create the second system to be in the state A. So we can't put the second system into the state psi 2A in general, while still leaving the first system in also the state A. This is called the no-cloning theorem. In this proof of the no-cloning theorem, our initial state of the two systems is therefore the direct product state of system 1 being in state A and system 2 being in its prescribed starting state S. And we then imagine we have some operation that over time turns this state into the state where system 1 is still in state A, but system 2 has also been put into state A. And this operation is just some time evolution operation that we can describe by some unitary linear operator, we'll call it t, such as this one here. This is a kind of unitary operator that describes a time evolution of a system when we have a Hamiltonian in here that does not itself explicitly depend on time. And this is the difference between the finishing time and the starting time. So whether it's this formula or not, whatever the machine is that takes the starting states and turns them into the final states is something that, since it is presumably quantum mechanical, is just described by some linear operator corresponding to the time evolution of this whole system, the measurement apparatus, and these two systems 1 and 2, all considered as one entire system. We presume then we've engineered our cloning system to give T the required properties. And we know for sure that we need at least two properties for T. First, we want T to perform the operation that if we start out with system 1 in state A and system 2 in state S, then we will end up with system 1 still in state A and system 2 also in state A. Second, if we choose some orthogonal state for system 1, another state B, we also want this machine, this cloning machine, to put system 2 into state B. So if system 1 starts out in state B, system 2 starts out in its prescribed starting state. We want the ending state to be that system 1 is still in state B and system 2 has been put into state B. There's no problem in general with constructing such a T, such a machine that would do this kind of operation. The problem comes when we want to clone a linear superposition state. Suppose the initial state of system 1 is the linear superposition that is an equal superposition, for example, of state A and state B. These are two possible orthogonal states of system 1. So, for example, we'll put this system 1 into this equal linear superposition. Hence, the initial state of the pair of systems is this total state here. System 1 is in this state, and system 2 is in the prescribed starting state. We can also multiply that out here. By postulation in quantum mechanics, the operators are linear. Operating on a linear superposition must give the linear superposition of the operations. That is, operating on a linear superposition like this must be the linear superposition of the operations considered separately. That is, T operating just on this state plus the effect of T operating just on this state. And we've got our 1 over root 2 out here because we had it here. Now, that is going to give us the following result, because the effect of T operating on this state we looked at before was indeed to put system 2 into state A, and the effect of T operating on this state was indeed to put system 2 into state B. We know that at least the machine has to do those two operations if it's going to be a cloning machine. But this state is not the one we wanted for our cloning operation. What's wrong with it? We wanted our cloning operation to take the system 1 superposition state and change system 2 from its initial state into that superposition state. We wanted this to be the final state of system 2 because that would be a clone of this initial state in system 1. And we also want it to be a clone, so it has to leave system 1 also in this state. Well, that overall state would be the following one. It would take the initial state here and turn it into this one. it would therefore have system 1 in this superposition state, the one it started off with, and system 2 put into that superposition state. We would have a half out of here because of these two factors multiplied on the bottom line. But we did not get that state from our machine. We got this state. So if we designed our machine correctly to perform these operations that we've seen before, the individual operations on cloning states A and state B, then it does not correctly clone the superposition state. The linearity properties of the quantum mechanical operator have determined that if we got the cloning properties we wanted for the individual states A and B, we did not get the cloning result we wanted for the superposition. This result is not special to the particular superposition we chose. Any other superposition would give us a similar wrong answer. Hence, though we could in principle make a device to clone specific basis states, that device could not clone superpositions of those basis states, and hence we cannot make a device that will clone an arbitrary quantum state. We can use this no cloning property to ensure the security of communications through quantum cryptography.